Hello and welcome to the first in a new series of lectures on the topic of understanding science. My name's Colin Frayn and I decided to create this lecture series because what science actually is, as opposed to what it produces, is surely one of humankind's greatest achievements. In fact, I would go as far as to say that the process of science is, in itself, a far greater achievement than any of its individual discoveries. And yet most people have never been taught this, the secret of how the human race learns. If you think about it, that's fairly odd, given that in our 21st century world pretty much every aspect of our lives is dominated by the findings of the scientific community. This course is not about the deep theoretical knowledge required to build a computer chip, or to put a human being on the moon. If you're interested in that stuff, then that's great, but that's not what this is about. I won't assume any detailed background knowledge because I want this course to be accessible to as many people as possible. I'm interested in explaining the actual workings of the process of science. What is science, and why is it the way it is? In this first lecture, I'm going to talk about the concept of proof in science, which is, after all, what it's all about. What does it mean to discover knowledge, and what are the limits on our inquiry? I want to start out by talking about the real background to science. And you notice on this slide I'm writing science with a lowercase s. That's because I want to make the distinction between the process of scientific inquiry, science with a lowercase s, and the profession and practice of science in the real world, science with an uppercase s if you like. I think this is something that's often missed when people learn science at schools, that there may be many facts and figures to learn, but far more important is the actual thought process underlying this. Why did people come up with those facts? How did they come up with those facts? And why are they important? This is extraordinarily valuable to every human being, no matter what profession you choose to follow or what direction your studies eventually take you in. Science is a process for gaining knowledge about the world around us. It's one of many such processes, but it's the way which has been tuned with the single aim of finding out the truth as accurately and efficiently as possible. There are other ways of investigating the world around us which don't have this aim. Guesswork, for example, is a way of investigating the world around us, but it's unlikely to lead to any particularly profound discoveries. That's not to say that guesswork will never give the correct answer. After all, if you guess for long enough, you'll eventually come up with the correct number for the age of the Earth, say, but you won't have any confidence at all that you've got it. In other words, there's no way to tell the difference between an accurate and an inaccurate answer, and this measure of certainty is extremely useful. A method for investigating the world around us not only ought to get us as close as possible to the correct answer as quickly as possible, but it should let us know how confident we should be about our answer. Likewise, we could follow our intuition, which is great for understanding how billiard balls might collide with each other and bounce around a billiard table, but isn't much use for probing the microscopic nature of the inside of the human cell, or the structure of the universe at its largest scales. In fact, intuition often gives precisely the wrong answer, such as the famous case that most people imagine that a cannonball should fall faster than a feather, but if we can ignore air resistance, they both fall at exactly the same rate, as Galileo showed. Alternatively, we could rely on some ancient writings to get all our knowledge of the world, which you may or may not find useful in personal matters of morality or family values, say, but it's not going to tell us at what time the next total solar eclipse will happen, or how to put a satellite in space, or which chemical compounds might combat malaria. So it's only of limited use in the modern world. Science is very different to these methods. As I said, the aim of science is not to go for the simplest or the most comfortable answer, or the one that seems most obvious and is easiest to understand. No, science is driven by the desire to know what's true, and to know how confident we can be in the answers we find. A little later in this course I will be talking about the scientific method, the process underlying scientific discoveries. But before then I'm going to talk through some of the core concepts that interest us as scientists. Today's lecture on proof is at the very heart of what science does, because all of science is essentially attempting to prove whether any given statement about the nature of the universe is true or false, and how confident we can be about that answer. So science works by building up hypotheses, or tentative explanations for events that we see in the real world. It then attempts to collect evidence either for or against those hypotheses, which might be actual physical evidence discovered in a laboratory or through a telescope lens, or it might be evidence in the form of a theoretical model which would explain whatever phenomenon we've observed. The details don't matter just yet, and as I said I'll go over them in a lot more detail later in this lecture series. But for now, what's important is the general picture, that science works because it asks itself the question, how might this be wrong? As I said, the driver behind all scientific inquiry is the search for the truth, and other considerations like the time it takes us to find that truth, or how much we might like each proposed explanation, don't really come into the equation. So science is a process which aims to explain what we see in the universe by generating hypotheses, which are tentative explanations, and by attempting to prove or disprove them by gathering evidence in the most trustworthy way possible. And the only way it can really do that is to take humans, especially our intuition, out of the picture as much as possible. But science also requires a few other assumptions if it's ever to get off the ground, and it's those that we must come to next. In order to do science, and by that I mean to do any science at all, in fact, in order to learn anything reliable about the universe in any way whatsoever, you have to make a few assumptions. And here are the 3 fundamental assumptions that science makes. And remember that science is just a mechanism for learning about the universe, and it's the best way that we've ever come up with, so other methods for learning how things work pretty much all have to assume these same 3 things, and they do a worse job in the end. So, firstly you have to assume that there's something to learn. And that's to say, you have to assume that the universe works according to some unchanging underlying laws. Laws that you can learn and laws that don't just change randomly from day to day. Of course, this is obvious in a sense. If the universe didn't work like this, then anything you learned on day 1 would be completely and utterly useless on day 2. So the process of attempting to learn anything at all would be impossible. And in fact, we have pretty good reason that the universe obeys this first assumption, merely because the accumulated knowledge of centuries of scientific progress seems to actually be getting us somewhere. If the universe changed underneath us, then experiments that were performed to discover fundamental scientific principles 3 centuries ago in the day of Newton would no longer work the same way today. The gravity that Newton discovered might be completely different to the force that acts in the universe today, but it isn't. Moreover, we can be reasonably certain that the underlying laws of the universe are at least constant in time because of the study of the universe at its largest scales, known as cosmology. Thanks to the finite speed of light and to the marvels of the largest modern telescopes, when we look at very distant objects, we're seeing them as they were a very long time ago, and hence we can probe the earliest epochs of the cosmos from the comfort of our very own planet Earth. And when we look at these distant objects, we notice things behaving back then just as they do now, according to the known laws of physics. So that's at least encouraging progress on our first assumption. Secondly, we have to assume that our senses give us some kind of real information about what's actually going on in the universe. This seems like a strange thing to say because to most people it seems obvious that our senses tell us accurately what is actually happening. After all, that's what they're for, isn't it? If our eyes gave us fictional and inaccurate view of the world, then the ability of sight would be completely and utterly useless. But this is actually a fairly difficult question, about which top philosophers enjoy debating in extraordinarily complex and convoluted ways. If you think about it, when you dream, everything seems real to you at the time. But the universe in dreams behaves very differently to the universe that we see when we're awake. Sometimes we can fly, or we can walk through walls, for example. But who's to say that we're not dreaming right now? Who's to say that we're not just brains in jars in some mad scientist's laboratory, wired up to various devices designed to insert into our minds the false delusion that we're actually in this universe, with laws that operate in a certain way, when in fact the real universe outside is totally different. So we could all be living in some kind of elaborate simulation with fake laws of nature that any self-respecting mad scientist could easily program to work in any way he or she wanted, and which need not even be remotely similar to those in the real universe. In other words, who's to say we're not in the situation depicted in the Matrix films? This is one of those questions that we just have to ignore if we're going to do science. In fact, we have to ignore it if we're going to learn anything at all about the universe. Just like the first assumption of constant underlying laws, we can't possibly know anything with any conviction at all unless we assume that we're able to actually get information from the outside world into our brains in some sort of reliable way. If we can't assume this, then there is no point in attempting to learn anything in any way. Again, this isn't just science, this applies to any system of knowledge whatsoever. Nothing works unless we assume these 2 points. And unfortunately, there's no way to prove either of these 2 assumptions, at least rigorously. They seem reasonable, of course, as I hope you agree, but we can't prove that they're true beyond any possible doubt. So that's the first 2 assumptions. The third one is a bit different, and it's a really important one, so I'm going to spend a little while longer on it. In fact, this isn't an assumption that we need to make in order to trust our understanding of the universe. It's an assumption we need to make in order to make it possible to describe our knowledge, to write down what we've learned in a way that's useful to us and to others. And that assumption is the assumption of simplicity. Now, this might seem like a strange thing to assume given how complicated modern science can be with quantum theory, relativity and so on. But what I mean by this is that we need to assume that whenever we see something happening, we can assume the most general explanation possible for what we've seen. For example, if I pick up a stone and drop it and it falls, then I pick it up again and drop it again and it falls again, then I repeat this 100 times with the same result every single time, it seems fair to derive, at least tentatively, the general law that stones fall when they're dropped. In fact, it seems sensible to assume that the same stone would fall regardless of who dropped it, for example, or where they dropped it, or when they dropped it in time. That is to say, the most general explanation, that stones always fall when dropped, by anyone, anywhere, at any time, is the preferred one. We have no evidence to suggest that stones might fall differently when dropped by a child compared to an adult, for example, or by a man compared to a woman, or that they might fall more rapidly when dropped on a Tuesday compared to a Friday. So we always make the assumption of the simplest and most general law that explains our observations. This simple rule is known as Occam's razor, and it's so fundamentally important I think it's worth spending a few minutes covering it in more detail. So, when you started listening to a lecture about science, I'm willing to bet that you didn't think I'd be talking about a 14th century Franciscan monk. But that's exactly who enters our story at this point. William of Occam is a fundamental figure in modern science, not because he made any particularly important scientific discoveries of his own, but because his name is attached to one of the core underlying principles of the scientific method. Occam was something of a polymath, as most great thinkers were back in his day, and he contributed to a number of fields from theology and philosophy through politics and logic and natural sciences. The principle of Occam's razor, ascribed to him, though probably never explicitly stated in any of his works, is simply that we must always take the simplest explanation for any given observation. The rationale behind this argument begins with the simple fact that there are always an infinitely large number of explanations for any observation that we see. For example, if I happen to notice that when I drop a piece of wood in a bucket of water it floats, so I could generate a tentative hypothesis that says that all objects float in water. With a bit of experimentation I might notice that stones don't float in water, and neither do chunks of lead, for example, so I would narrow this hypothesis down to just a subset of things that float in water. But no experimentation could ever rule out the possibility that these objects only ever float in water in years prior to the year 2300 AD, say, and that after that date they will sink. I can't possibly ever make the experiment that will test that eventuality, or the possibility that it will work up to the year 2301, or 2302, or 2303, and so on. But does that mean that it's impossible for me to deduce anything useful from my experiment? Well, not at all. Occam's razor simply says that we must take the explanation that requires fewest extra unproved assumptions, and that's the most general case. Let's take another example. Isaac Newton's most famous discovery, arguably, was the principle of universal gravitation. That is to say, he discovered that the same force that holds us on the Earth and makes an apple drop from an apple tree is the same force that causes the planets to fly in their vast orbits around our Sun. Newton wrote down an equation that could enable us to calculate the gravitational attraction between any two bodies of any size. So, for example, we know that two human beings standing a metre apart exert roughly the same gravitational force on each other as the Earth does on a mosquito on the Moon, and other interesting nuggets of knowledge. But you notice that Newton could have added any number of extra conditions to his famously simple law of gravitation. For example, the force of gravity between two bodies is proportional to the product of their masses and inversely proportional to the square of their separation, except for giraffes on Mars, in which case it's twice as strong. I defy you to disprove that hypothesis. It's completely in agreement with every single measurement that has ever been taken of any gravitational force ever in the history of the human race. But that doesn't mean that it makes sense to propose it on equal grounds to the much simpler version that Newton himself came up with. Occam's razor allows us to go for the simplest solution again, and that's why it's so valuable. So, to recap, Occam's razor says that we should always go with the simplest model that we can in order to explain an observation. But what do we mean by simplest? Well, it's the one that makes the fewest assumptions. Any assumption that we make is essentially a guess for which we have no decent evidence. And if there's no decent evidence, then there's a good chance that we might be wrong about it. So the more of these assumptions we make, the more likely it is that our model is wrong. That's not to say it is wrong, or even that we have any direct evidence to prefer it over our more general model, but merely that it has a lower chance of being correct. In a later lecture on Bayes' theorem, I'll look into this concept a bit further, but for now, let's look at how two brilliant minds have described Occam's razor in their own words. Isaac Newton wrote, "We are to admit of no more causes of natural things than such as are both true and sufficient to explain their appearances." I think this summarises the concept rather well. Bertrand Russell, the famous 20th century British philosopher, put it slightly more technically. Whenever possible, substitute constructions out of known entities for inferences to unknown entities. By that, he means that it's a fair and reasonable decision to prefer models containing only things that we know to be possible or true, over those about which we have absolutely no idea whatsoever. After all, it's always possible to come up with a crazy model that explains any measurement perfectly, provided you're allowed to include, say, a highly intelligent and undetectable alien race that messes around with your apparatus without your knowledge. But even though that fits any data you could ever obtain and does so perfectly, it's clearly neither reasonable nor helpful. And to repeat what I've said before, without assuming Occam's razor, no useful knowledge can ever be gained about anything, ever, by any process. I know it's fairly bad form of me to start off a lecture series on a subject that I love, trying to convince you that it's one of the greatest ever achievements of the human mind, and the first thing I say is that you have to accept these three assumptions without any decent proof, or else there's no point going any further. But that's exactly what I am saying, and I think I've demonstrated why that must be the case and why it's entirely reasonable to do so. So much of what we do as humans makes colossal assumptions that we are in no way justified in making, but we make them nonetheless, and I think we can judge by the fruits of our actions whether those assumptions were in fact correct or not. And I think that science, by its extraordinary progress over the last few centuries and the staggeringly huge positive impact that it's generated for the human race, has more than demonstrated that the assumptions we make bear extremely valuable fruit, and that's good enough for me. And now, with that part over with, I can spend the rest of this course actually looking at the way that science works and how we should interpret scientific results. And I'll start by introducing a really simple and important concept that I reckon is misunderstood by probably the majority of even the most intelligent people in the world today. I'm going to introduce the way I see the process of science working. It's an illustration that makes sense to me, and I hope it will make sense to you too. Admittedly, it's rather high level, but it's often a good idea to get a high level view of a subject before diving into the details, and this idea is what I will call the spectrum of certainty. You see, I've misled you ever so slightly so far by claiming that science is all about finding out what is true and what is false. Of course, that's the ultimate aim of science, and it would be great if we could attain that level of certainty about our scientific theories, but in practice, science is almost never able to show whether something is absolutely true or false. And that might come as a surprise to you, because you've probably been told throughout your school days that that's exactly what science does. But in fact, it's not quite that simple. Any objective claim that we can make about the universe is either certainly true or certainly false. But whether or not we can prove that, that's another story. For a start, the vast majority of all claims are completely outside of our sphere of knowledge. We have no proof of whether they're true or not, and in some cases we can never have such proof. The claim that some planet outside our own solar system might harbour intelligent life, for example, is one where we have no proof, and it's entirely possible that we will never find any such proof, especially if that claim turns out to be false, because we can never search every single planet in the entire universe. Claims about the past might be similarly outside our realm of access. For example, we may never know exactly what the lost plays of Sophocles were all about. They are forever lost, and we have no way of finding out that information. The philosopher Bertrand Russell came up with a now famous example to illustrate this notion. In his own words, "If I were to suggest that between the Earth and Mars there is a china teapot revolving around the Sun in an elliptical orbit, nobody would be able to disprove my assertion, provided I were careful to add that the teapot is too small to be revealed even by our most powerful telescopes." Russell goes on to use this as part of an argument against dogma, challenging the idea that just because we can't prove that something is false, it doesn't mean that it makes sense to accept it as true. However, the illustration serves to illustrate a more general principle, that there is a very large family of claims that we cannot prove or disprove, but which lie somewhere on the spectrum between these two extremes. And right in the middle of that spectrum are those claims about which we can have no opinion whatsoever. Let's look at those three categories of proof. I've just said something that you might regard as rather controversial. I said that science very rarely, perhaps never, proves whether a claim is absolutely true or false. So let's look at this assertion in more detail. There are things that we can prove are absolutely true or absolutely false. In general, though, these belong to the fields of mathematics or logic. For example, we could all come up with some examples of claims that are certainly and provably false, such as 1 + 1 = 3, or 10 is less than 5. There are, of course, far more complicated ones, such as Fermat's last theorem, which states that there are no positive whole numbers a, b, c, and n which fulfill the relationship written here, if n is greater than 2. And now that this theorem has been proved by the mathematician Andrew Wiles in 1995, we can say that the claim that such a set of integers does exist is definitely false. And we can also state the results of any other mathematical claim, such as the claim that there exists a pair of whole numbers a and b which, when you divide one by the other, gives the square root of 2. This seems a bit arbitrary, but there's a fairly simple and important proof that this claim is definitely false, and that therefore the square root of 2 is what's called an irrational number. This is particularly important because we haven't exhaustively tested every single possible pair of numbers for which this might be true. Of course, there's an infinite number of them. We've proved instead using mathematics that there is no logically possible such pair of numbers. If you're interested, the proof isn't very long and you should be able to find it quite easily on the internet. So in maths there are lots of claims that we can class as definitely false. Similarly, there are lots that are definitely true. So 1 plus 1 is definitely equal to 2, 10 is definitely greater than 5. Pythagoras' theorem for calculating the longest side in a right-angled triangle using the lengths of the other two sides, written here as a squared plus b squared equals c squared, a favourite of high school mathematics teachers. This is also definitely true. And then there is the class of sound logical deductions. By that I mean any deduction where you take two facts that are true and combine them in a logically consistent way to produce a third fact that must therefore, by the rules of logic, also be true. For example, if I said that all humans breathe oxygen and that I am a human, both of which I'd like to think are true claims, then the deduction that I breathe oxygen must also be true. This last one gives some ideas of things that science could actually prove to be true or false. Any claim that can be investigated by examining every single relevant possibility and checking them all against the claim. So one can make a scientific claim that there are no human beings over 3 meters tall. If we measured the height of every single human being, then we could show that this claim is true or false. But if you think about it, most claims are not of this type, and this particular case is really more a matter of surveying and measuring than actual scientific inquiry. We can only say that a claim is definitely true or definitely false if there is no logically possible exception. That is to say, there is no way we could be wrong. There is no exception, however incredibly unlikely it might be. So mathematical proof will work by examining all possibilities that could logically occur and proving that a given statement holds for them all. But science only rarely has access to this method. Almost all scientific claims are not exhaustively searchable. For example, the idea that I introduced earlier that perhaps the theory of gravity might change at some undetermined point in the future. Newton's law of gravitation seems to work very well for pretty much every single measurement that we can make today, but there are many measurements that we can never make, such as checking what will happen in 1,000,000 years' time. We have no reason to believe that anything will change at that point, but it's logically possible that it might. And so, despite the fact that Newton's law of gravitation has been tested time and time again and shown to be correct, we can't say that it's definitely true. In fact, Newton's law of gravitation is an excellent example, because pretty much all of Newton's laws were modified ever so slightly by the special and general theories of relativity discovered by Albert Einstein in the early 20th century. Newton could never have known it, of course, but when he wrote down his famous law of motion, stating that a force applied to an object produces an acceleration proportional to the force and inversely proportional to the mass of the object, in other words, if you push things, they move, if you push heavy things, they don't move quite as much. It turns out that this becomes increasingly inaccurate as we approach the speed of light, as Einstein showed. Newton's law didn't include this specific exemption because he had no reason to do so. After all, he had no evidence that the speed of light was even vaguely relevant. It's not that Newton was really wrong, it's just that what he discovered was not, after all, a universal law of gravitation, but an approximation to it. A very accurate approximation, as it happens at low speeds, but an approximation nonetheless. Just like, as far as we know, the current law of gravitation that we use might be an approximation which ignores what happens after the year 2500, say. So that's claims that are perfectly true or false, but finally for this slide we have the class of claims about which we can have no opinion whatsoever. Those that are precisely in the middle, exactly neutral. My assertion here is that this is an empty set, that there are no such claims. But we'll come to this in more detail when I cover Bayes' theorem in a later lecture. For now, I'll just leave you with that tantalising suggestion and move on to looking at scientific proofs. As I said on the last slide, science can only very rarely claim certainty, and even then it's usually only for the most trivial of claims. This means that scientific theories are almost always tentative. We must always be open to the possibility, however unlikely, that our theory might turn out to be false. Whatever our theory, it is only ever backed up by a finite set of measurements to prove it, and unless we've exhaustively searched every logically possible situation in which our claim could be tested, then there are always more measurements that we could take, and any one of those new measurements might disprove our theory entirely. Does that sound a bit negative? Well, don't worry, because the rest of this presentation is the good news. As I've said, this is all about the spectrum of certainty, and that means that there are more than just the extreme values. Just because we can't be absolutely certain that a claim is true or false, it certainly doesn't follow that we should be neutral about it. As Bertrand Russell showed with his theory of the celestial teapot in orbit around the Sun, it's very easy to make up a claim that we can't completely disprove, but which nonetheless is very unlikely to be true. It would be a highly irrational decision to remain neutral on the question of Russell's teapot. The process of science does something extremely valuable that I touched on earlier in this lecture. It assigns probabilities to hypotheses. A hypothesis is a tentative claim about the universe, one that has not been proven certainly true or certainly false, but which nonetheless has some merit in it that makes it worth investigating. Science allows us to work out how likely these ideas are to be true or false. I probably ought to say that even some bits of maths fall into this category too. For example, there's a famous mathematical problem called the Riemann hypothesis that says that a certain set of numbers, which are all solutions to a specific mathematical equation, all have a special property. The details of this don't really matter for the purposes of this illustration, but it so happens that nobody has ever proven that this hypothesis is true, that all of these numbers have this property. In fact, it's an open problem for which there is a very substantial cash reward for anyone who finally proves it. All mathematicians, or most mathematicians at least, suspect that it's very likely to be true, but it's not yet proven. Now we can quite easily test this set of numbers one by one to see if they all satisfy the required property, and we can do that very quickly with a computer, and it turns out that at least the first 10 trillion of them all satisfy it just fine. But that's not a proof, because there's infinitely many of these numbers, and we can't possibly test all of them. However, the fact that so many of them have all behaved exactly as expected can at least make us very confident that this hypothesis is probably true, even if it can't prove it to the satisfaction of pedantic mathematicians and the like. Science works very much like this. For example, let's take a claim such as, the sun will rise tomorrow. Now that's not a fact, despite what you might think. If it were a fact, I could put it at the far right-hand end of this line, the spectrum of certainty, just here, along with mathematical claims like 1 + 1 = 2 that we looked at before. But the thing is that I can come up with logically possible circumstances in which the sun won't rise tomorrow, and I can't disprove them. For example, it might be that a highly powerful alien race will invade our solar system and destroy the sun completely in an hour's time from now. Or it might be that we're completely wrong about solar physics, and the sun is actually about to die of its own accord overnight. Those are both logically possible and would stop the sun from rising tomorrow, but I dare say you won't lose much sleep over them, or at least I hope you don't. My aim is not to give you more ridiculous nightmares. The reason why these possibilities don't trouble us is that they're both, as far as we know, extremely unlikely. We've taken a very large number of measurements of the sun rising every morning, and it's never disappointed us. We have no evidence whatsoever of any alien race existing, and even if one did, there's no evidence that it would be hostile. And even if it was, then there's no reason why they might wish to destroy our sun, or even that such a thing might even be possible. And even if all this was true, and they wanted to destroy the sun and they had the ability to do it, there's no reason to believe that they're going to do it in the next few hours. And as for the other suggestion, that the sun might just die of its own accord, well, the theories that we have about the evolution of stars are very, very thorough and well evidenced, and match the observations that we take very closely. So I think we can be reasonably sure that our star has many billions of years left to live, exactly as the theories predict. So we've got a very large body of evidence suggesting that the sun will rise tomorrow as expected. And I think it's fair to say that it's pretty much certain that it will do. Not absolutely 100% certain, but practically certain. By which I mean it's as close to certain as we really care about. There are other theories in this class too. For example, we're pretty sure that special relativity is correct because we've measured its effects lots and lots of times in varying circumstances. In other words, we've tested a wide sample of the potential circumstances in which we believe it should act, and in those tests it perfectly predicts and explains our observations. But again, it's not inconceivable that special relativity is just another approximation to something yet more complicated. Or it might well be that tomorrow the observation will be taken that will cast serious doubt on Einstein's theory as a model for our universe. Similarly, we can see things like the age of the Earth, which has been extremely rigorously and repeatedly shown to be around 4.5 billion years, and we can be incredibly sure that its age is therefore in this range. Certainly it's more than 4 billion years old, to an extraordinarily high level of certainty. And then there's also the Riemann hypothesis that I mentioned earlier. Well, what about the other end of the scale? Well, there's claims that oppose our existing models of science. Newton's theory of gravity, as I mentioned earlier, has been very well attested in a range of circumstances, and it's never been known to reverse, it's never been known to stop pushing objects away. But that's not to say that it won't do exactly that tomorrow, due to some weird underlying quirk of physics. But again, catastrophic though it would be, nobody's losing sleep over it because it's so unfathomably unlikely. And then there's the claims of the paranormal. We can't absolutely prove that such things don't exist, but we can certainly say that all the allegedly paranormal phenomena so far detected can easily be explained by a combination of very natural human factors, and so on. So at the ends of the scale there are theories that are very, very likely, or very, very unlikely, and then there's everything in between. So how do we work out where our theories should lie on this scale? In a later lecture, I'm going to talk in much more detail about the scientific method, and I'll explain how we investigate hypotheses in a reliable way. For now, let's see if we can at least tie in this concept of the spectrum of certainty with the whole idea of scientific investigation. I've said a few times now that I think there's no such thing as a claim that we're literally neutral about. The reason for that is that we never go into any scientific inquiry with zero knowledge. We always have at least a tiny bit of information about any process that we investigate. Let's say that someone comes up to us claiming that they're able to play chess to Grandmaster standard. That's not an impossible claim, but Grandmasters are few and far between, so it's probably unlikely. However, let's say that this person has come recommended and someone else has said that they're an extremely strong player. So we have a slightly positive view of their claim to start with. That is, we think it's more likely than not to be true. So it would lie somewhere here on our spectrum. Next, we play them a few times at chess and they completely demolish us. We get a friend who is a strong club player and they demolish her too. So we shift our certainty even closer towards true. Maybe this person really is a Grandmaster. After all, we haven't proved that this person is a Grandmaster yet, but they're certainly performing in line with what we would expect. However, next we notice something very strange. We notice that this person is wearing a cunningly concealed earpiece. We listen into that earpiece and we hear the voice of an accomplice in a hidden room who's sitting with a powerful chess computer feeding moves into this alleged Grandmaster's ear. Well, this turns the tables completely. The theory that we once saw as rather likely we now see as unlikely. The person was probably cheating. That explains exactly how they are able to beat our other strong players. We confiscate the earpiece and we readjust our expectation downwards. Note that we're still not certain that the claim was false. Maybe this person is actually an excellent chess player, but they were just wearing the earpiece for some other reason. So we set them up with a few more games, and make sure they're not wearing any kind of listening device. And this time they lose every single game. We offer them a considerable sum of money if they can win a game against the same club player that they easily beat before, and this time they lose to her in minutes. Our evidence is building, and now we're nearly certain that this person is actually not a Grandmaster at all. We've hardly disproved it entirely, because they could still be faking a lack of skill for some reason, but I think this investigation has now passed a certain point, a threshold, past which point we can quite comfortably discard the claim that our subject has Grandmaster skills as being false. In summary then, the process of science is really the process of moving arrows about on the spectrum of certainty, as it were. In theory, we start with no knowledge, though in practice there's always some. We gradually add information and continue to adjust the probability that our theory is true, until we pass some threshold that is sufficiently tight for our requirements. Importantly though, we never stop moving the arrow. Just because it's gone past the threshold, that doesn't mean that new evidence won't shift it back out again. For example, if we manage to set up a game in which our subject cannot possibly cheat, and now, for some reason, they manage to beat a couple of strong players whilst blindfolded, then the arrow is going to shift all the way to the right-hand side again, close to the true end of the spectrum. We're still taking into account all the evidence we've gathered so far, but this new evidence is so strong that it counteracts the rest. The model that we had before, namely that our subject was attempting to cheat his way past our test, can now be replaced with a new one. Say that our subject was creating an elaborate ruse to make it look like he had no talents at chess at all, when in fact he is a very strong player after all. And this new evidence is strong enough to overturn our previous opinion. You already know lots of scientific theories. The theory of gravity, the theory of relativity, the theory of evolution, germ theory, the Big Bang theory. You may never have given it much thought before, possibly because the word theory has a very special connotation in science that is actually quite different to its common usage. Ordinarily, when we say that something is just a theory, we usually mean that it's a guess, perhaps with slight backing from limited evidence, but it's certainly nothing that you would put any money on. However, in science a theory is a very different creature altogether. Theories are the foundation for organising scientific knowledge. And as you can tell from the list I gave earlier, theories are not just tentative guesses, they're very much more solid than that. A scientific theory is a model which attempts to explain some aspect of our universe, and is strongly supported by evidence, usually by an overwhelmingly large amount of it. Theories should make predictions about how the universe should behave, without which they really aren't much use to us. But predictions are much more important than that. They mean that a theory is potentially falsifiable. This is what the great philosopher of science Karl Popper famously declared in the middle of the 20th century, which in his view was one of the key properties of a scientific theory that separates it from a guess or conjecture. It's really important that a theory sticks its neck on the line, as it were, and makes predictions that, if they turn out to be incorrect, would disprove the theory. Or at least, if they turned out to be incorrect, then we would need to either modify the theory or shift it to the very left-hand end of our spectrum of certainty, into the very unlikely section. So Newtonian gravity has stuck its neck out on many occasions and predicted exactly how objects should behave. For example, every time we put a rocket in space, we're testing whether Newtonian gravity works as a theory, and every time it turns out to pass that test. In fact, pretty much every second of every day we're conducting trillions of parallel tests of gravity, when we watch inanimate objects continue to stay standing on tabletops pulled down by gravity instead of floating off aimlessly into space. Though even with all these tests, Newtonian gravity was never certainly true. It was always a scientific theory, not a fact. For example, as we saw earlier, Newtonian gravity does make a few errors when making specific predictions, especially concerning certain objects in space, and that's where Einstein stepped in and proposed some corrections with general relativity. So at that point we learned that Newton's theory was not universally true, but it still remains an excellent approximation in nearly all cases. Likewise, germ theory makes predictions, namely that whenever we find an infectious disease we should find some kind of pathogen, like a virus or a bacterium, that occurs alongside the infection in the affected patient, but not in healthy subjects. If we were ever to find an infectious disease that was not caused by any pathogen, then that would be indeed strange and might constitute a disproof of germ theory. Given how much germ theory has given us, and given the complete lack of any other possible mechanism for transmitting disease between hosts, it seems extraordinarily unlikely that germ theory will ever be disproved. So biological scientists would talk about it as if it's true, as if it's 100% certain, which it most likely is, but we can't prove that absolutely. The theory of evolution also makes countless predictions. Though we can't go back in time and rerun the history of life on Earth, we can investigate the genetic codes of the animals on Earth today, and lo and behold, they look exactly as we would expect, having shared a common ancestor in the distant past. Had we discovered that our genetic codes were all incredibly different, or if we had completely different chemicals comprising our genes, or if the Earth had turned out to be too young to allow for enough time for evolution to run its course, or even if we discovered that our genetic code was so short it couldn't possibly encode an entire animal, then that would all have disproved evolution. So evolution as well stuck its neck out many times, and many times has it been absolutely correct. So consequently, it also deserves the honoured status of a scientific theory. Time to wrap up. I've covered a huge number of things in this lecture, so I want to bring them all together now and remind you what we've learned. First of all, I think a wonderful way to look at science is to see that essentially what it's doing is attempting to shift theories around on this spectrum of certainty. In other words, it's assigning probabilities to hypotheses. Whenever more evidence comes in, the process of science adjusts the likelihood that any related hypothesis is true or false. In order to do this, in fact, in order for humans to learn anything whatsoever about the universe around us, we absolutely must make a few assumptions about that universe. If you remember, the ones that I mentioned were that we needed to assume that the universe had some sort of underlying order, that we could actually learn, and that it wouldn't change randomly every so often just to confuse us. Secondly, we need to assume that our senses tell us something accurate about the universe. And thirdly, we need to use a principle of simplicity such as Occam's razor, so that we can actually codify our observations into useful models. I think that the majority of this lecture is dedicated to showing that there are actually very few things in science about which we can be absolutely 100% certain. That's just not what science is about. Just as we can't totally disprove the existence of Bertrand Russell's celestial teapot, I can't guarantee with absolute certainty that the theory of gravity won't be totally disproven tomorrow by a single bizarre celestial event. Absolute certainty is more or less exclusively reserved for mathematics and logic. But in science we can get close enough. That is to say, we can gather so much evidence in favour of a certain hypothesis that it passes a threshold of reasonable doubt. and it becomes practically certain. That is to say, even though it's not absolutely certainly 100% true, it's near enough. And we can make that threshold as narrow as we possibly desire. If you gave me a gun, for example, with 6 chambers and told me to insert one single bullet, spin the barrel, point it at my head and pull the trigger, and if I lived I would win £1 million, I still definitely wouldn't do it. It's just not worth the risk. But if that gun had 1 trillion chambers and 1 bullet, with the same potential prize fund, then I definitely would, because a 1 in a trillion chance is so close to 0 that I don't need to worry about it. Just as I'm writing this, scientists across the world are trying to work out why an Italian experiment seems to have shown a certain kind of particle called a neutrino having travelled faster than the speed of light, something that Einstein's theory of relativity says should be impossible. But Einstein's theory is so well attested and so thoroughly demonstrated in so many different ways that the overwhelming likelihood is that it will turn out that the experimenters have been mistaken in some way. But if that extraordinarily tiny possibility turns out to be true, if Einstein is wrong, and the experimenters genuinely discovered something new, then science accepts the changes, moves on, and develops another theory, an even more accurate one, to replace Einstein's. And the only reason why we can do this is because Einstein's special theory of relativity makes a few very important, testable predictions. It puts its neck on the line and says, if this theory is correct, then the universe must behave like this. So that if we discover that the universe doesn't behave like that, then the theory cannot reasonably survive in its present form. Remember, though, that a scientific theory is much more than just a guess. It's an entire encapsulated model of one aspect of the universe, together with plentiful supporting evidence from numerous different sources. And it is with such key elements that the towering edifice of science has been gradually built up over centuries of thought and investigation. In this lecture we've talked a lot about this process of sliding hypotheses along our spectrum of certainty, and constantly bringing in new information so that we can update our opinion of where each hypothesis should lie. But how exactly does that process work? Well, that just happens to be the subject of my next lecture in this series, on the subject of Bayes' theorem. So watch this space, and I hope we can continue this journey into the world of scientific thought together. In the meantime, I'll put the notes for this lecture up on my blog at frayn.net, where you can also follow the other many and varied projects that I'm working on, and you can leave your comments and questions. In particular, if there's an aspect of science that you don't understand, then drop me a note and I'll see if I can produce a presentation on that very subject. Thanks very much for listening, and I'll see you next time.